Okay, so we're going to get started, and we will let people trickle in as they do. Can you hear me okay in the back? Yeah? Good? All right. So for those of you just joining in this lecture, my name is William Hamilton, and this is Applied Machine Learning, Comp 551. And today, after a bit of a light introduction, we're going to jump into some more math today and talk about linear regression. So just before jumping into the material, some logistics revisited and reiterated for those who weren't there and also for those who were at the last lecture. So everything in this course is either going to be on the course website or on my courses. So the course website is where you're going to find the schedule, the links to lecture slides, that's very important, homework materials, readings, etc. So the link is there. The link is also on my courses. And then my course is going to be used for announcements, quizzes, grading, discussions, and there is now a discussion forum for trying to find project partners, because this course is going to involve 4 projects, all in groups of 3, where at least one member of your team has to change every time. So this will be a useful place for those of you who don't know 12 people to be able to meet up and try to find partners. And another important thing, for those of you who maybe are less familiar with Python, so everything in this course is going to be pretty Python focused. The mini projects, we're going to ask that you do them in Python. The final projects, we're going to recommend you do them in Python. So there will be tutorials next week. These have been shifted back by an hour compared to what I said last week to accommodate conflicts. So there's 6 to 8 p.m. on Tuesday in this room, 6 to 8 p.m. on Thursday in the Otto Maas building in room 112. These are the exact same tutorial twice, so you only need to go to one. They just have 2 of them because people have constraints. Yeah? Pardon? Python 3. Yes, let's just everybody use Python 3. I think is the easiest thing to do. That's what the tutorial will be in, and that'll save headaches in terms of TAs not having to debug Python 2 versus Python 3 issues for you. And as we'll go through in the tutorials, we're also going to highly recommend people use some things like Google Colab notebooks and things like that, which, as you'll see in the tutorials, are really useful things you can use where you don't actually need to even install all of these packages on your local computer, but can use some remote servers provided by Google. So one final logistical note before we get into the content. So I mentioned these quizzes a few times. So as I said in the first lecture, there will be 2 online quizzes on my courses a week. These are auto-graded quizzes. There's one that's going to be available from Tuesday, basically at, I think, basically right in the morning on Tuesday until midnight on Wednesday. So you have 48 hours. Once you start the quiz, you get an hour. And then there's another quiz that's available Thursday, Friday. These 2 quizzes aren't identical. And there's 2 of them because, say you do the first quiz and it's way harder than you thought, then you get a day or 2 to study and you know what material is going to be in the next one. It's not identical, but the questions are going to be really, really similar. So it's to give you a chance, and we're only going to take your best grade between the 2. So if you get 100 on the first quiz, you don't need to do the second quiz. And these are going to start next week, but because we're still in an add-drop period, the next week's quiz don't actually count towards your final grade, because it's unfair to people who are new to the course. But these are going to be really important, these first quizzes, A, just to get people familiar with the system, and B, these quizzes are kind of like self-assessment quizzes. They're going to be somewhat challenging, and especially on kind of the mathematical fundamentals that I'm going to be presuming people have related to probability, related to calculus, and related to linear algebra. So if you take these quizzes and you were really stumped, it's maybe worthwhile to reconsider maybe taking this course in a later semester. So they're there. Again, next week's quizzes, not counting towards your grade, but highly recommend everybody does them because they're really good self-assessment. Even just want to just go and look and see what the questions are, and you're like, oh, I totally get this. That's fine. But they'll be there for you. Okay, so that's all I have on logistics. Any questions at this point? you asking if I'm planning on uploading the lecture slides before lectures. I actually do not plan to do that. I will post them within 24 hours, but I like to have the opportunity to, in the worst case, maybe correct any things that were raised or add things if there was questions people had. So I prefer to upload them afterwards. So yes, they will be up right away. Lectures are recorded. There were some technical issues in the first lecture. Should all be resolved now. It's a great question. So their question is, do we have to use your own hardware for deep learning things? Yes and no. So we have a limited amount of Google Cloud credits that have been given to us. Unfortunately, that's not enough to have everybody be able to run crazy GPU experiments for deep learning. And these are going to be most useful for the final project. So generally, we're going to ask that for the mini projects, we expect you to use your own hardware or use the hardware that is available in the CS department, like the lab machines and things like that. That's, of course, going to limit you in terms of the kinds of models you can build. But everybody's on at least an even footing there. And ideally, we want to use these Google Cloud credits, the ones that we have for the final projects. And when we get to that point, we'll have a Google form where people can submit what the project is they're doing, why exactly they think they need Google Cloud credits. Because if we just give equally to everybody, sadly, it's not very much to do anything fun. So we'll try our best to allocate them in a fair way, but some projects, some really, really good projects, don't require a lot of compute power. And I'm also going to recommend to people for final projects to not choose to try to replicate, say, Google DeepMind's most recent result, because that could require compute power that's just not really available even with these credits. There's quite a big variance, so I would say that it depends. If you want to actually buy hardware, hardware is quite expensive. GPUs, the state-of-the-art GPUs that are very popular for deep learning are thousands of dollars. There are AWS and Google Cloud instances you can rent, and for hundreds of dollars or even tens of dollars. There's really a huge spectrum. But if you're talking about a paper published in one of the top machine learning conferences this year by one of the big labs, that probably is, I would say, hundreds to thousands of dollars on average of compute power. So I don't expect you guys to spend your own money on that. And again, there's a lot. That's why when we get into the final projects and the mini projects, I'll go into more detail. But I'm going to talk a lot about that interesting things isn't just running really big models. It's actually doing more interesting experimentation. So we're going to really recommend people not to choose these big, huge, compute-intensive projects. Okay, awesome. So now jump into the actual content. So today, we're going to be talking about supervised learning. I mentioned this in the last lecture. And just to refresh, the basic idea behind supervised learning is that we are given a set of training examples. So say a row in this table shown here at the bottom of the slide. So in terms of notation, we're going to have a training example which will denote xi. So this is the ith training example. In this training example, we're going to have a bunch of different features. And we're going to denote the jth feature of the ith example by x subscript ij. You have to forgive me. I'm going to overload subscripts a little bit in this lecture and throughout the rest of the course. It'll always be obvious from context whether or not we're referring to a training example or a feature, but just as a heads up there, it can get a little funky. And then the other important thing is our output or our target. So we're trying to use our input features. So here we're trying to predict, say, the outcome, whether or not a tumor is going to recur. We're going to use our input features, say the tumor size, the texture, the perimeter, its shade. We're going to use all this information to try to predict, say, whether or not this tumor recurs or the change in size for this tumor. And what we're going to learn formally is a function f that's going to map our input features to our output target. And formally, we call f the hypothesis. I'll usually call it a model, but in kind of more formal statistical language, we would often call this the hypothesis. So in terms of prediction problems, as I mentioned in the last lecture, there's two major types of supervised learning prediction problems, the first being classification. So here, for example, we're trying to predict whether or not a treatment is successful versus unsuccessful, whether or not a tumor reoccurs. So the important thing is that our target, our output, is a discrete or categorical set. So most often you'll see what's called binary classification. That's where we're just predicting yes or no, so 0 or 1. The other important type of supervised learning, and what's going to be the focus for the lecture today, is called regression. So here the output is a real number. So for example, say we're trying to predict the change in size in a tumor over time. This would be a regression task. Our output is a numerical value. And we also have different types of features. So we have different types of outputs. Those can be categorical for classification, or those can be numerical for regression. But for our features, they can have different types as well. So for example, we can have numerical features. These are going to be the focus for today because they're the easiest to deal with, and we'll talk more about kind of feature engineering and things like that later in the course. So these are straightforward. They're just numbers on the real line. We can also have categorical features. So categorical feature in this case might be, say, the texture of the tumor. So say there's 5 different types of texture. There could be, say, rough or smooth and some other categories. And then a third type of feature that you won't see as much, but that is worth mentioning, is ordinal features. So these are categorical, but where they're ordered. So say a ranking, first, second, third, fourth. And again, today we're going to be pretty focused on just numerical features, and later on, in a few lectures' time, talk about how to actually encode and deal with some of these more complex feature types. So an important statistical assumption that we're going to need to make when we're doing supervised learning in general, and especially supervised regression, is this idea called the IID assumption. So this stands for the assumption that all of the training examples, so every row in our training set, each one of these examples is independently and identically distributed. So by independently, what we mean is that one row doesn't depend on another row. These are a bunch of independent examples. These patients aren't connected in some way. This is important because if there's actually correlations or connections between our different data points, this is going to break a lot of the statistical assumptions behind our model. And the other aspect of this is the identically distributed assumption. And what this means is that we're assuming that all of our data points are coming from the same distribution. Of course, this is not always going to be exactly true in practice, but it's again an important statistical assumption. What we're assuming is that the distribution that we're sampling our training points from is the same for all of our examples. And why is that a reasonable or a necessary assumption? Well, intuitively you can think if we don't make this assumption, then, and we train our model on a bunch of examples, then the next thing we see could be completely unrelated, not coming from the same distribution at all. So we need to make this assumption in order to really do any kind of machine learning. So given this assumption, what we're going to do formally is what's called empirical risk minimization. So the idea is that given some function class, and I'll describe concretely a function class in just a second, what we're going to do is try to find the best function in this class that fits our data. And how we do this is we define some notion of error. So left intentionally a bit vague right now, but the idea is that we have some notion of how bad we are at predicting our target using our features, and we call this our loss function, or the error function. And when we're doing empirical risk minimization, this is the exact thing that you might expect we do, which is we just want to find the function in our function class that minimizes this error over the training set. So we have the number of mistakes we made within a particular sample within our training set, and what we want to do is let's find the function that minimizes this error. And this is really 90% of all machine learning, is trying to minimize an error on some sample, some training set. So for example, we might have a very simple regression task, so one shown here, where what we're we're trying to do is use the x values, so use the x-axis values, to try to predict the y-axis values. So we have some observed values x. These are our features, so we have just one-dimensional features. They're numerical. And we're trying to predict these y values, again, a numerical target. So this is the simplest version of supervised regression. And the question is, what kind of model should we use to fit this data? So what should our function class f be? And today, what we're going to focus on is linear models. These are the simplest, well, one of the simplest function classes. They're also probably the most important type of models in machine learning, and they're really the foundation for a lot of the rest of this course, and all of deep learning is really built on top of these linear regression models. So a linear function, quite simply, just means that our prediction, so our prediction function f, our model is just a linear function of our features. So what we have is here we have m different features, and we're just taking the sum of all these times a weight for each of these feature values. And we also have this w0. This is called the bias or intercept. And what this does intuitively is this allows us to actually just shift our function up or down, shift a bias, basically. And for the rest of this talk, and just to simplify notation, we're always going to assume that there is a dummy feature value, which is just a constant value for everything, just a 1. And then this means that we don't need to separately consider this intercept term. It just means that we have an extra feature that's 1 for everything, and the weight we learn, or the parameter we learn for that feature, is our bias or our intercept. So the question here is, how do we actually determine what these weights are? So we're saying that our output, our prediction, is just a linear function of our input features, but what exactly is this linear function? How do we actually learn that? And the way we do this, the fundamental technique that, again, is really going to come up throughout this course, is this idea of the least squares solution. So again, we have this linear regression problem. We're trying to find the best linear function f so that we can predict some outputs y. Now, there's many different ways to define a loss or to say how good the function we've chosen is. So when we're trying to determine these weights, we need to have some measure of our error, how good we're doing predicting this output value. And there's a variety of different choices, but the one that is, in some sense, the most popular, but also for statistical reasons that I won't dive into now, is a very reasonable thing to do, is to use what's called the squared loss. So what we're saying is that our error, given some chosen parameters w, our error is the squared difference between our predicted value and the true value. So our idea is that we want to minimize this squared difference. So why aren't we just taking the absolute difference? Well, because that's a bit tricky because it's not differentiable. Why aren't we just taking the difference? Well, that's weird because we don't want to treat positive errors different from negative errors. All we care about is whether or not we're off from predicting the real true value. So again, our goal here is to find a linear function f such that we minimize this squared loss. So we call this the least squared solution. And what we're doing here is we're finding the function that when we sum over the n training examples in our data set, we minimize the squared difference between the true target value for each of these examples and our predicted estimate, which is just a linear function. So the easiest way to denote this linear function is just a dot product between the weight vector that we have and the feature vector for each instance. Any questions at this point? Yes. Oh, is it? Oh, this light. Oh, yeah, probably. Oh. Oh. That's too dark. that one's flashing. Unfortunately, they only can be all controlled together, so we can either go flashing or we can have a kind of a dark room. Dark room? Alright, dark room it is. Alright, that's okay for everybody? Alright. Okay. So, this is the least squares solution method. And a bit of intuition, what does this look like? Well, this is probably what you were expecting. We're finding the best fit line. So, in our previous example where we had this simple one-dimensional input vector x and this output y, the least squares solution is just this line shown here on the left. It is basically the line that fits through all these data points. And to get an intuition for what this intercept term meant that I mentioned a bit earlier on, this intercept term determines how far up we are shifted from the axis. And now, in higher dimensions, it gets a bit harder to visualize this, but for example, if we had a two-dimensional input space, then our linear best fit is going to be a plane, and so on. So this tells us what we want to do. What we want to do is find this linear function f that minimizes this squared error. We want to get this least squares solution. So how do we actually do this? Well, it's a bit easier if we rewrite things a little bit and start using matrix notation. So the first thing we can do is we can write the prediction for our entire training set as just the matrix X. So X is going to be the matrix that contains all of our input data. So it has n rows. Each one of these rows corresponds to each different training example. It has m columns. Each of these columns corresponds to a different feature. We have our y vector. This is the vector that has our targets, our predicted values for each training instance. And then we have our weight vector. This is an m-dimensional vector that when we multiply the training matrix, the data matrix, by this weight vector, we get our prediction for all of the different training points. And if we want to write our error, this squared error, in this vector notation, it is shown just here. And quite simply, we're just taking the y outputs minus the data matrix times the weight vector, and then transpose times the same thing on the other side. Now, we've got things in matrix notation. Now the next step is to actually find the function that minimizes this. So what we want to do is we want to find the weights that give us the minimum value for this function. Now here is where a bit of the calculus comes in. And what we have here is, well, really a system of m equations and m unknowns, but probably the easiest way to think about how we're going to solve this is what we want to find is the minimum of this error function. And this is going to be one of the extremum of the extremal points of this function, which we can get by taking the derivative with respect to the weight vectors and then setting that derivative equal to 0. Of course, you might say to yourself, well, this also could be a maximum, so when we find points where the derivative is 0, this isn't necessarily a minimum, but you can convince yourself here that in this case, we're actually going to get the minimum value when we set this derivative equal to 0. And we'll talk about kind of more formally why that's the case a bit later on. Okay, so now we have this function we're trying to solve, so we're trying to set the derivative with respect to the weights of this loss function equal to 0. So now what we do is we can just apply a little bit of algebra, do some rearranging, and what we get is that our estimated value for the weights, so our estimate of what is the weight values that minimizes this squared error, is given by this equation here. So it's x transpose x, taking that whole thing to the inverse, times x transpose, and then times y. And then now that we have this, we can then make our predictions. We can predict what are the likely or our predicted values for the targets just by taking this estimated weight matrix and multiplying it by our data matrix. We can also make predictions for new data now. So we have estimated this weight vector, and now we can use this weight vector to make predictions. We just take a training example, multiply the feature vector by these weights that we've learned. So to give a concrete example of this, returning again to our very simple example where we just have some one-dimensional x inputs and some one-dimensional y outputs. And now our goal again is to estimate this weight matrix, and we do this by, again, taking the data matrix x transpose times x, take the inverse, and then multiply this by x transpose times y. So here, giving some actual numbers, what we would do is we would take these two, this data matrix, multiply the data matrix transpose times itself, and note again that we've added this dummy row of all ones to account for the bias or intercept term. So we can compute this. We also need to compute x transpose times y. And then finally we can solve, say, using our favorite linear algebra software or by hand, and we would come up with the best fit line, which is that our estimate, our predicted value for y is that y equals 1.6 times x plus 1.05. Or visually, the line that I showed you before. So just a quick aside on if you were to actually do this sort of linear regression using a software system, so using something like R, something like scikit-learn, other sorts of stats packages, which we'll describe in more detail later on, but I just wanted to point out now that I'm giving a pretty high-level description of this, and generally when you're going to be doing linear regression, what you're going to do is you're going to have a bunch of features. So here this is showing examples from an actual prostate cancer data set, where we have some features related to the weight, the age of the patient, a bunch of different indicators, and we're trying to predict the output level of a particular enzyme. So oftentimes, just in terms of terminology and things you'll see when you're working with linear regression tools, is the one thing you're going to estimate is what's called the coefficient. So this is just another term for the parameters, or these weights, this W that we're learning. So we would learn the coefficient, say, for the age of the patient is this number that tells us how does increasing this particular value, say increasing age, what is the impact of that on our output y. The other thing you're going to get if you run an off-the-shelf linear regression package is you'll often also get estimates of what's called the standard error. I'm not going to go into details of how to compute the standard error now because we have a lot to cover today and in this course, but it's important to know that this standard error is something that tells us how confident or precise our estimate of this weight value is. So this tells us how predictive of the output a particular feature is. So what this means is that if we have a large coefficient, a large estimated value for one of these parameters, and we have a very small standard error, this means that we expect a small change in this feature value to have a really big output, really big impact on the output. And I mentioned this because ideally we would have time to go into a lot of the statistical details surrounding, say, how we can compute statistical significance related to linear regression. These are some things I'll touch on a little bit later on. But I just want to flag these things here because I want to make sure that we don't get into, say, bad practices of misunderstanding the output of linear regression. And one of the really important things to watch out for is that the size of the coefficient, the size of the estimated weight value on its own doesn't tell you how important that feature is. All that tells you is that this feature might have a large change, but if it has a really huge standard error, then we have no confidence in that estimate. So in some sense, coefficients don't really tell you about importance, and that's actually something you get from standard error, or if we were to go into more detail, from actually computing things like p-values. Okay, so that's a brief aside. We'll return to a bit more statistical best practices later in the course. So now we're going to consider the computational side. So that was a bit on the statistical side. But now we're going to talk a little bit about the computational cost and also a technique that allows us to do this in a way that's maybe a bit more computationally efficient. So the first thing we have to ask ourselves when we're trying to compute the computational cost of linear regression is what operations are actually necessary. So overall, what we need to do is we need to perform 1 matrix inversion and 3 matrix multiplications. So we're computing, again, X transpose X. This is actually going to be the most expensive of our matrix operations, of our matrix multiplications, because remember, this data matrix X is n by m. So since X transpose is now m by n, what this is going to cost us is n times n squared operations. And for those of you who are really into the complexity of basic operations, we can do matrix multiplication a tiny bit faster, but here we're not going to worry about that. So what's important is that we're about n times m squared operations. But the thing that's really expensive here is this inversion. So we're inverting an m times m matrix, and that's going to cost us m squared, or m cubed, sorry, operations. And just so people don't get totally lost on m's and n's, it's important to remind ourselves what is m and what is n. So m is the features, the number of features in our data set, and n is the number of training examples. So generally, actually being m cubed isn't so bad, because generally we're going to have much fewer features than we do training examples. And so in general, it's not so bad. So say we had just 10 different features, this isn't going to be so expensive. This is not going to break anyone's budgets and require Google Cloud credits. But at the same time, it's useful to know that in general we have this polynomial complexity, which is not so bad. But if we're handling really, really huge data sets where we have tons of features, and this starts to be a thing once we start getting further into things like deep learning, computational complexity can maybe still start to be a bit of an issue. So now we can ask ourselves, is there a more efficient alternative? Well, there's no real way to totally avoid all the computational costs we need to do here, but there is a neat trick which we can use, and this isn't just kind of a one-off trick. This is actually going to be one of the fundamental algorithms of this entire course. And this is the idea of that instead of trying to just find some closed form solution, we're actually going to find a way to instead have an incremental learning algorithm. And so we recall this least squares solution we came up with, where after we took the derivative of our loss function with respect to our weight vector, and we set this to 0, we were able to solve this using some linear algebra and figure out that to get the predicted value, or to get our best estimated weight vector, we just take X transpose X, all that to the inverse, times X transpose Y. And this is something I'll call the closed form solution. So in this case, we were able to explicitly just compute what the exact optimal parameter vector was given our loss function. But this is not always going to be the case. And the other thing is that X can also be so big that it's just ridiculous to try to compute this closed form solution explicitly. So what we're going to do to get around this is we're going to go back to this gradient step. So recall that the way we came to this closed form solution was we took this matrix, this vector representation of our squared loss function. So again, this equation down here is just what tells us what is the average squared difference, or the sum of the squared differences between our predictions and our targets. And we took the gradient of this function with respect to our weight values. And this gradient was equal to this down here. And we set this to 0, we solved this, but now we're going to take a step back, and we're instead going to think about the fact that this gradient actually tells us how to move the parameters, in which directions we should move these parameters, so that we can maximally increase or decrease the error. So ideally we wanted to set this thing to 0, but if you think about this thing in terms of it being a vector, it's a vector that's pointing us in the right direction, where we should shift our parameters in order to increase or decrease our errors. Ideally, of course, decreasing our errors. So if we want to run gradient descent for this mean squared error, so MSE is often the abbreviation we'll use here, what we might want to do is actually just produce a sequence of weight solutions such that the error of these solutions gets smaller and smaller for every step that we take. And how are we going to do this? Well, given the last slide, the obvious solution is that we're going to use the gradient. We're going to take steps in the direction that's given to us by the gradient. So how does this algorithm work? This is called the gradient descent algorithm. And the gradient descent algorithm is how everything works in deep learning. And the basic equation here is given an initial weight vector. We start with a random vector. We start with all zeros. We'll go into details about how to initialize these things later on. What we're going to do is just for a number of steps, we're going to take our previous weight vector, and to get a new weight vector, so to get w subscript k plus 1 from our previous one, wk, this is just that weight vector minus alpha, some parameter we're going to determine, times the gradient. And then we stop this whole procedure once we stop moving. So we have some tolerance, epsilon, and we say once we've stopped making any significant changes, our vector is not really moving anymore, let's call it a day. So again, the important thing here is that we're finding a good weight vector, finding a good solution to this linear regression problem by taking a step in the negative direction specified by the gradient. Because again, we want to descend the gradient, which is why it's called gradient descent. And this parameter, this alpha that I mentioned here, this is the alpha that determines what we call the step size, or the learning rate. So whenever we're taking these steps at every k, we're moving according to the direction of the gradient, and how much we're moving is determined by the step size alpha, which is often also called the learning rate. Any questions at this point? Yep. Oh, down here? So this is just telling us that like when we need to stop. So this is something you have to set kind of problem specific, but say we might want to say like epsilon equals 10 to the negative 6, and say once our weight vector, the absolute difference between our new weight vector and our last one is less than 10 to the negative 6, we're probably not learning anything anymore, and we can stop. I mean, if you want to be really safe, you could always set your epsilon to basically be something near machine precision, so you know you've really stopped moving, but then you might end up in an infinite loop. So there's no kind of one size fits all how to set epsilon, but it should be a very small number, usually something like 10 to the negative 6. It's a great question. So, and I also should repeat for those who want to watch things on recordings, the next question was, how do we actually set this learning rate? And in fact, this is the next slide. So it's a good transition where whether or not this algorithm actually works, in fact, depends on how we set this learning rate. So we can't just randomly set it. It has to be set in a reasonable way. And why is this the case? Well, intuitively, we can think about if the step sizes are too large, we're just going to oscillate forever. We're just going to kind of walk all over the place. So this suggests to us that ideally, these alpha k's should decrease over time. So at the beginning, we might want to take really big steps. But once we're getting close to the solution, we probably want to slow down a little bit. But on the flip side, if our steps are too small, we're just never going to make it to the solution. It's just going to take us way too long. So a bit more intuition for what happens here. This is actually a really important thing. This is a lot of practical machine learning goes into setting learning rates and coming up with good schedules for how we deal with these learning rates. For linear regression, it's not so bad, but once we get to more complicated models, this is going to become a lot more of a challenge. And so the idea here is that if we have a learning rate that is too large, so I should quickly explain that we're supposing that this here is our loss function, and we're trying to get down to this minimum here. So suppose that we are going to take a step, and the direction that we should go to minimize this function, if we took the gradient, is we should walk over this way. But suppose that we had a really big learning rate and a really kind of adversarially bad learning rate. What could happen is we would take a step that would just jump us way over the other side here. And then if we took another step, we'd end up back over there. And in fact, if you have a learning rate that's too big, you'll always hit a point like this where you just jump back and forth, if the learning rate's too big and constant over time. So that's something we want to avoid. The other thing we want to avoid is just when the learning rate is too small, and in this case, all that happens is we basically don't go anywhere. It's a much easier to understand failure case. So all is not lost. There actually is a way to guarantee that we can set these learning rate values such that we will converge under some conditions, and in fact, we're going to converge to what's called a local minimum. And I'll explain that in just a couple slides. So these conditions, they're called the Robbins-Monroe conditions, and what they are is the first assumption is that we need that the sum, if we're taking the kind of infinite sequence of these alpha k, and it's important to note that alpha can depend on k, so alpha can get smaller as k gets larger. So we need this, the sum of these as we go to infinity to be infinite, but the sum of their squared values to be a finite value. So what kinds of functions actually satisfy this? Well, most simply, probably the easiest one is 1 over k plus 1. So we just have things, a learning rate that just slowly decays over time. There's other things you could use. If you have finite t's, you can use like 1 over 2 to the 2, so on and so forth. An interesting point, and I'll also kind of highlight these as the course goes on, is you might think to yourself, okay, so people who are real, applied machine learning researchers, they must always be checking the Robbins-Monroe conditions on their learning rates when they're training their models, and sadly that is not the case. Sadly, I would say that an extremely high proportion, at least the majority of papers that are published in machine learning use a fixed learning rate, or use an off-the-shelf scheduler that doesn't necessarily satisfy these conditions. And it's important to know these things, and it's important to keep them in mind, especially because when we're working with simple models like linear regression, you need to follow these rules, because then you'll always come to the exact right solution. But once we move into the crazy world of really crazy complicated models, it becomes less and less important to check these things, but still really important to know, and really important to know that there is a proper theoretical way to actually set these values. Okay. Any more questions at this point? Yeah. Okay, so the question is there any way to know like what is the kind of lowest error we could get? So basically an estimate of, say, how far away we are from the optimum. Sadly, generally this isn't possible. So oftentimes the terminology that's used for this is what's called an oracle. So if we had an oracle that could tell us like what is the lowest value we could get for say a linear function or a quadratic function or some other particular function class. So sadly, I mean, the challenge here is that if we had that, then we would have the best solution. So it's a bit of a chicken and egg issue. Occasionally, there is some instances where we might have, say, a function class that's pretty easy to estimate, like a linear function class, and something more complicated, and we know, well, what is the error for the best linear function, and that can give us a good insight for how we're doing with a more complicated model. Oftentimes in proofs we'll assume access to these sorts of things, but in practice it doesn't help us very much. This is a good point, and so we'll get into a bit more later on about how to estimate, in some sense, how well we're doing in terms of whether or not we're close to the solution, and other issues related to how well we're doing on the training set versus how well we're predicting on out-of-sample data. But one of the most useful things we can do as a good kind of proxy is by looking at this here. And this is going to be a little bit conflated by the fact our learning rate is changing, but in general, or actually even better than looking at this, what you can look at is the magnitude of the gradient. So the magnitude of the gradient is going to give us a pretty big signal of how well we're doing. Again, it's not always the case, but you can, in a sense, get a sense that you're close to the solution if really your model's not moving around very much anymore. But for linear regression, this doesn't matter as much in the sense that linear regression, we're always guaranteed to kind of pretty quickly converge to the right solution, as long as you haven't set your tolerance epsilon to something crazy or your learning rate to something crazy. And once we get to more complicated models, we'll also talk about kind of training best practices so that we can, make sure that we're kind of monitoring our models in the right way. Yep. This is a great question, which I will return to in just a second, but I'll see if there's any more questions before I move on to that one. Yeah. So yes, another great question. So maybe it's worthwhile to talk about that really quickly. So these conditions, where we have these Robbins-Monroe conditions, here we go. So these are always going to guarantee that we're going to converge to what's called a local minimum. This does not require really any assumptions. It requires an assumption that our function is continuous. Formally, we like Lipschitz continuity, what it's called. That's not something that's going to be on the midterm, but you do need to have some minor assumptions. But the important thing here is we're converging to what's called a local minimum. And why is that important? Is that this local minimum, the thing we converge to, isn't necessarily the best. So that's part of this first question. But it will be the best in the case where we have a convex question. So that's part of a convex function. So that's the answer to the next question. And so for those who are less familiar with convexity and these concepts, to give a little visual example is that we're supposing that we're trying to get to the local or the best place on this function. Now here, suppose we're actually trying to maximize it because that's a bit more interesting. If we were to get to a local maximum, we would either hit this point or this point. Both of these are local points where when we walk in either direction, we go down. But only one of those is actually the global maximum. So this is important because all that I've been talking about, this gradient descent function, these Robbins-Monroe conditions, these things guarantee that we hit one of these local points, but they're not going to guarantee that we actually get to the global best minimum for the error function. And this is something that is kind of a general problem that there's no easy fix for. One of the things you can do if you're really worried about this is that you can do a bunch of random restarts. So you can do gradient descent once, run the model, get to an answer, do it again, and odds are, say there's 10 local minima, if you run 100 times, you're going to hit them all. And you can just choose the best one. We'll get into more best practices about how to actually kind of, in these cases, choose a model in such a way that you do it sensibly. But an important issue is that this whole local minima issue is only a problem for what are called non-convex functions. So this isn't an issue if our function is convex, and for those of you who are familiar with this principle, you'll probably recognize that linear regression, or in particular this mean squared error loss function, is a very nice convex function. So this is not a problem for linear regression. If we run gradient descent for linear regression, we always hit the global minimum. We always hit the right answer. Not a problem at all. But the world is not always convex, and we will very quickly in this course start to run into things that are non-convex. So it's an important thing to know. And I'm not going to go into the kind of nitty-gritty details of the formal definitions of convexity. that is something that I expect people should be somewhat familiar with, but for today, we will suffice with this informal definition of a convex versus a non-convex function. So a convex function is a nice function like this, where we always are coming down to this one point here, whereas a non-convex function has a whole bunch of squiggles. It's a very rough, crazy landscape. And you will often hear people, when they're describing machine learning models, especially more complicated machine learning models, you'll often hear people using the term loss landscape. And what they mean by loss landscape, this is referring to kind of how rough, how crazy, how squiggly this loss function is. So ideally, what we want are really smooth, easy to optimize loss landscapes, but sadly that's not always the case. And again, there's one thing that's nice is convexity, but another thing that's nice is also kind of how rough or how continuous a function is. So this is a terrible function because when you're here, you're really high, and then all of a sudden you're super low, all of a sudden you're really high again. You can think about trying to run gradient descent on a function like this. You might take one step and get over here, and then you're like, okay, that was okay, then you're back over here, and then you're over in this basin, and this can get pretty rough to optimize. So just in terms of terminology, I'll use them a little bit. Yeah, we'll often call this the loss landscape, and we might talk about the basins within this loss landscape. So any more questions? We're running to the end of the formal content for this lecture, so I'm happy to answer questions if anybody has them. This is a good question. So can we use information from the derivative or from the gradient in order to kind of make sure that we're in a good part of the loss? Using just the first order gradient information, not really, because the first, so just taking the first derivative, that's going to tell us kind of which direction is the steepest ascent or descent. That doesn't really tell us anything about the other aspects of the curvature, but we can also look at the second derivative. That's going to give us a sense of the curvature. We can look at higher order derivatives, and these can be really useful. And in fact, you can solve linear regression with much fewer steps if you use second order gradient information. This is what's called the Newton-Raphson method. So this is something that can be very useful, but of course, computing second derivatives can be very expensive. And the other thing is you could think, well, couldn't we just estimate the gradient in a whole bunch of different places to get a good sense of the landscape? Well, you could do that, but that's going to be pretty expensive, and you may as well just run gradient descent rather than kind of getting this global view of the whole landscape. Yeah. Yeah, again, I mean, unfortunately, you're generally pretty so it depends. I think that if you have a reasonably nice function, so I should repeat the question, sorry. So the question is there any way to like a priori get a good sense of do you have a well-behaved loss landscape? Sometimes yes, because sometimes you write down a model and you explicitly write down that model so that it's convex. And that was much more of the case of machine learning, say 10, 15 years ago. People really like to come up with convex models, because convex models, we know the loss landscape is going to be nice. And then even some models that were maybe just, they were non-convex, but it was pretty easy. We could know by analytically looking at the form of the functions, we had some sense of what they looked like. And so that's sometimes you have that case where you look at the loss function, you look at your model, and you can say, okay, I know just analytically, I can even figure out what this loss landscape might look like. With the kind of current prevalence of much more complicated deep learning models, where we're stacking a whole bunch of functions of all sorts all on top of each other, it's really no longer possible to analytically figure out what the loss landscape looks like. Even just, we know most of these things are non-convex. It's pretty easy because we add in crazy nonlinearities. But yes, unfortunately, all you can do with a lot of modern machine learning is you can try to take a bunch of samples of the loss at different points, take a bunch of samples of the gradients, and try to paint yourself a picture of what it looks like, but again, that's pretty expensive if you have a really big model. Yeah. So what should you do when the cost function is too flat near the local minimum? This is a really good question, and this is something that we'll actually explicitly discuss a technique for this, so I'll just give a bit of a kind of precursor to it now. So the issue is that if the loss function is really flat near the minimum, what's going to happen is, so we're making lots of steps here, and then we get to near the minimum, and we could do better, but it's really flat portion of the space, and so it might take us a really, really long time to get there. The technique that's often used in that case is what's called momentum. So what you can actually do is, instead of just taking a step, you can also take a step that is partially determined by, say, the last k steps you took. So you're keeping intuitively some momentum around. So you're not just taking a new direction every time. If you've been walking this way for the last 10 steps, then you're going to continue with lots of momentum moving in that direction. And this momentum can be especially useful for dealing with very flat lost landscapes near the best point. All right, so that closes out the content for today, and now I'm just going to quickly refresh the things you should take away, things you should know. So the first really important thing that you should keep in mind is the definition and characteristics of a supervised learning problem. So what were the important things for a supervised learning problem? You have a data set. You have a bunch of input features. They can be a variety of kinds. Today we are just talking about continuous features or numerical features. And you can have supervised regression, where we're predicting a continuous or a numerical output, or supervised classification. We talked about linear regression, this idea of a hypothesis class, what an error function is, the algorithm that we can use for finding a closed form solution. And we talked about the issues with this closed form solution, the fact it can be a bit expensive, this computational complexity. Something didn't go in detail on, but another issue with the closed form solution is we did a matrix inversion. And for anybody who's taken a numerical computation course, you might be aware of the fact that matrix inversions can be pretty numerically unstable if you do them naively. And so building off of this, we talked about this gradient descent method. This is this general technique where we compute the gradient or the derivative, and then we're taking steps that allow us to descend to the minimum point of our loss function. A very fundamental concept. So these are all things that you should take away from this lecture. And for next lecture, we're going to continue talking about linear regression. Going to go into a bit more of the technical details. And in terms of a to-do list, so things that people should do between now and next week. So one thing I highly recommend doing, especially to get a sense of what it's like to actually work, say, with Python, is reproduce the linear regression example. So we had this example I went through in slides 18 to 29. Highly recommend just solving that simple example using a software of your choice. If you want to go kind of above and beyond, you can implement gradient descent, and that wouldn't be the worst thing to do because that is going to be something you need to do in the mini project. So if you want to get ahead of yourself and be very ready for the mini project, highly recommend reproducing that, implementing gradient descent. As I mentioned, next week there will be 2 quizzes. These quizzes do not count towards your final grade because we're still in add drop period, but they're going to be self-assessment quizzes. So do look at the questions, do try them. If you get totally stumped, it might be worthwhile to reconsider that you may want to wait until you've taken a few more math courses before you take this. Do go to the tutorial if you want to learn Python. There's recommended readings here. And finally, the midterm date and time. If you know you're not going to be here March 26th, please let us know right away, because there's a lot of you, and if we need to schedule alternate rooms, we have to do so. Thank you. Yeah. No, but it's good to have, but it's not required. Yeah.